Explanation of the double-slit experiment in Threads and Spinons Theory 1. Threads and spinons, physical basis threads, the unbreakable elastic threads of the electron expand and stretch as it moves through the experiment. These threads remain continuous, interacting dynamically with the environment. Spinons, rotational units embedded in the threads, provide energy and structure to the electron. The number and configuration of spinons influence the electron's interactions and the resultant light energy output. 2. Passage through the slits, interactions and effects when the electron approaches and passes through the slits, thread expansion and interaction with slit material. The threads stretch due to the electron's velocity and interact with the threads of the slit material. This interaction causes deflection. The slit material threads exert forces on the electron's threads, subtly altering their trajectory. Energy redistribution. Spinons within the electron's threads interact with spinons in the slit material, creating localized disturbances and realignments of thread tension. Thread interference beyond the slits. After passing the slits, the threads of the electron expand further and overlap. The degree of overlap determines areas of constructive interference, where thread tension aligns and amplifies destructive interference, where thread tension cancels out, creating low energy zones. 3. Formation of the pattern on the wall. When the threads reach the wall or detector, energy concentration at impact points, the stretched threads contract upon interaction with the detector surface. This contraction releases stored energy accumulated during expansion and interaction with the slits. Localized spinon stacks. Spinons, as energy carriers, concentrate in areas of high thread density. These stacks transfer energy directly to the wall material. Emission of energy and visible effects. The wall atoms absorb the energy from spinon stacks, causing excitation. The pattern's brightness correlates with the density and energy of the threads at specific points. Frequency and color of light. The frequency of light emitted is determined by the number of spinons in each stack. High-density regions with more spinons result in higher frequencies and brighter areas. Physical pattern development. Regions of constructive interference, high thread tension, generate brighter spots due to concentrated spinon energy transfer. Regions of destructive interference, low thread tension, result in dimmer areas or no visible emission. 4. Key factors influencing the pattern thread dynamics. The electron's velocity determines how much its threads stretch, influencing the pattern's interference and spacing. Thread tension and alignment dictate where energy is concentrated on the wall. Environmental interference. The threads of the slit material create disturbances that further modulate the electron's threads, contributing to the complexity of the interference pattern. Spinon behavior. Spinons moving along the threads carry rotational energy. Their distribution and interaction with the wall define the emitted light's frequency and intensity. 5. Observation and thread collapse. When an observation is introduced, thread contraction. External observation disrupts the thread's expansion, forcing it into a contracted, single-path state. Energy redistribution. Spinons align along the contracted threads, eliminating the interference caused by thread overlap. No interference. Without overlapping threads, the pattern simplifies into a single impact trajectory corresponding to particle-like behavior. Key adjustments and insights. Well-defined energy transfer. The observed pattern on the wall is explained as a result of thread contraction and spinon energy transfer. The brightness and spacing reflect thread density and spinon stack energy. Role of slit material. The slit material contributes to the interference by exerting forces and introducing additional thread and spinon interactions, amplifying the complexity of the final pattern. Observable light. Light is redefined as spinon stacks interacting with the detector material, with the frequency determined by the number of spinons in each stack. This enhanced explanation should be more convincing and comprehensive, clearly linking the thread's expansion, spinon behavior, and environmental interactions to the pattern observed on the wall.